All right, wow, it's great to be here today. I wish that I could look out the windows and see how beautiful Moraine Lake is and that I'm just kind of in and out. So still, to be in the Rockies and to see all the beautiful nature around us is actually quite incredible. I want to talk about what this last year looked like in Canada with the forest fires that we had experienced. Like 0.3 gigatons of CO2 was emitted into the environment. 18 million hectares of forest went up in smoke. It was a record forest fire year that we had. And now I want to put it in a context about, what does it look like in terms of global energy inefficiencies? Roughly 4 gigatons of CO2 was emitted into the atmosphere due to electricity inefficiency globally in the last year. That's 257 million hectares. That's 70% of Canada's landmass. So, forest fires were bad. This is way worse. So, I'd invite you to consider why we're all here and what we're really thinking about solving and the impact that we can have. So, my talk today as the founder and CEO of Arcus is coming from a place we've been building machine learned models for a decade and solving problems in energy cost management. And we operate across North America today with a global mandate to solve for $30 billion in energy inefficiencies and to find a way of abating 500 million tons of CO2. So let's go back a little bit and talk about AI for a moment and how digital adoption is going to become a big accelerating technology in grid transformation today. It's nothing new. Go back to like 1950, you had Alan Turing, you had Colossus, we won the war, we solved the code problem with the Nazi code, and then over a 40-year period, we had great contributions to, energy technologies with looking at how fuzzy logic, neural network models coming in, optimization around renewable technologies. All these things have been great, and that's AI. But what really happened was about 15 years ago, 20 years ago, we had cloud computing show up. And cloud was awesome because what happened was industry and large consumers everywhere found a place to store their data. Great, all right. And microprocessing became a thing. So now we could do rapid transactions, we can utilize artificial intelligence, and we had an environment to share all this information. So what we're seeing here is the additionality of all of these technologies. It's Moore's law, right? And we're going to the spot where, our rate of innovation is accelerating rapidly. And so when we start to look at digitization of grids, and what can happen is it stands on top of these technologies, our ability to transform these systems becomes very apparent. And really, I think the only thing that really gets in the way of the innovation is ourselves and our ability to accept the change that can happen in front of us more readily. So when I look at how this affects the grids that we operate in today, I look at it in an economic lens, first of all. The biggest economies in the world, India, China, the US, it's no secret. Big gross domestic product, big consumer of energy. We all know this. And then we have a whole bunch of countries that are on the struggle bus. They have access to low energy resources, and their GDP suffers. And a big part of the energy challenge is, well, let's add new generation, let's solve for this capacity problem, give everybody access to electricity. Well, excellent, sure, but that's not the whole story. We're competing with rising demand. Today we're at, I think roughly 28,000 terawatt hours globally consumption. Conservatively, we increase 18% to 36,000, 35,000 terawatt hours in the next 7 years. And gross estimates put us up to 60,000. So how are we going to match up with that when not only are we struggling with growing demand, our systems are actually not as efficient as they once were. The top OECD countries, Germany, Canada, the US, Right now, with every new installed megawatt of capacity on the grid, they're getting less and less output in terms of gross domestic product. So we have to look towards digital adoption and how we're going to solve for these energy inefficiencies to take the kink out of the curve and find a way of accelerating this. So we look to things like VPPs, and what does that really mean? I mean, you have at the center of it a technology that's AI-driven and enabled to provide insights to distributed generation sources so that they can interact with grids more efficiently. And to make this all happen, you need a couple of things. You need the DERs, so you need the prosumer who's starting to take advantage of adding behind-the-fence generation and other resources and evolving their own systems and participating in markets. You need intelligence as a way of giving insights so how they can determine how they're going to function in markets in relation to how their own facilities operate. And then they also need things like a friendly regulatory environment to enable them to participate in markets and to transact more efficiently. Like in Alberta right now, for those of you in the market, there's things like net settlement instructions that can enable the buying and selling of generation of load in near real time. And that's a market mechanism that's friendly towards these sorts of, evolved processes that we're going to see. But what it really comes down to is, I think, market enablement, the ability for the prosumer to participate in the ISO through demand response, capacity, load balancing, and then even in-market transactions where they can take advantage of trading and things like that is going to become part of the future. And it will become part of the future because they're getting access to the technology that they need to make decisions on their own for managing their energy costs. So on the bottom left in this chart, you have over-the-grid trading. So this is kind of the state of some of the Fortune 100, 500 companies in the market where they have some trading group, like take Dow Chemical, for example. And actually, they're probably further along the chain here, but they're able to hedge and manage their volatility. They're able to put other resources into the grid. They're able to pick what sources of energy they're buying, and they can green their portfolio. These are all really important things in managing their costs and managing their sustainability mandates. But through the utilization of more technologies and having insight as to how the market functions, and in a near real-time manner and short-term manner, they can evolve their thinking and start to add in resources, backup resources, behind-the-fence generation, and participate in the grid in even more meaningful ways. Demand response becomes part of their operations, providing import-export from their own facilities becomes part of it. But they really need an intelligent layer to do this effectively. There's the old way of doing it where you have somebody sitting there and pressing a button. Really works when you're looking at sort of predictive maintenance around equipment wear and tear and how you're managing all your behind-the-fence capital costs and things like that. But so much of the management and reducing, let's say, 30% of your energy costs comes from how you participate in the market. So forget all the stuff behind the fence for a minute and realize that the thing that is going to have your business survive through commodity downturns is understanding how the market impacts your business in real time. So this is this is where Arcus came from, right? Like we saw that challenge and that's what we wanted to step to. And then you see the evolution of these fully independent microgrids, and I mean, this is where they're their own independent system and they can interact, well, instantaneously and harmoniously with grids, and everything is really slick and transactions are, instant, and you really just need somebody there when things break. There's not a lot happening there right now. The market is somewhere between this, over-the-grid trading and partly independent microgrids. And fully independent microgrids, there's some examples in Germany, Australia, Japan, where you're starting to see these programs roll out. But a lot has to be done there, and it's very expensive to getting there. This is more like a UK cost breakdown, but if you're in Alberta, you can say that, like, 25% of your costs are wires or energy costs. You pay a premium to your retailer, and then the taxes is more like your wires and distribution charges, for purposes of this discussion. But you can look at over-the-grid trading and how somebody participates in just looking at an index, and they can generate savings just by looking at their arbitrage. They can generate savings by sidestepping energy market volatility, but they're using forecasts in the market, and they're using dynamic tools that lever AI to help give them the decision-making tools that they need to solve for that. When we look at independent trading and these microgrids that are starting to evolve, I think a really good example is looking at a couple of the seaports, the Port of San Diego. They were able to reduce their energy costs by 50% through the installation of behind-the-fence generation and participating in the market. So there's a lot of upside when you consider, the investment is worthwhile, and especially if you're thinking of renewable sources of energy to getting there, it goes a long way in saving money. And here, fully independent systems, well, yeah, you have a big financial gain here, but a big investment cost. And it's an evolution of the sum of the first two, really is what it is. But the technological hurdles that we have to getting over there aren't quite there, I would say, in markets. One, because of regulation. Two, because hardware enablement. And there's a few things that have to happen, I think, for the markets to evolve to this state, especially in North America. I haven't had a lot of time to go through this all in great detail. I wish that I had a lot of time, but if I could leave you guys with one thing, is to say that as these markets evolve and digitization in grids starts to unfold in our market, the drivers behind us, AI, microprocessing, cloud computing, all the technology for rapid transformation is here. And the savings are real. You can see that the opportunity of solving for the challenge in global inefficiencies is worth like $500 billion a year. So, and it's worth a lot to the environment. And I think that's why we're all here today. So anyway, I kind of want to wrap with that. And yeah, it's been fun. So thanks, guys.
Stay up here, Dan, because we're gonna have 5 minutes of questioning, and then we have 2 more keynotes to come up with the same strategy, 15 minutes per keynote, and then 5 minutes of questioning. So if I could have the runners with the microphones, if we have some questions from the audience for Dan, that would be fantastic. Going once?
I get away scot-free?
Oh, man, that's because you answered all their questions. Okay, well, Dan, thank you very much.
Actually, Dan.
Oh, we got somebody?
Can you unpack 12.5%? Because quite honestly, I think that number's low.
It is low by design because it's easy to answer to a low number, and it actually is probably more related to just what line losses would be across inefficient systems globally. It's generation, consumption, and what the delta is between the two.
But outside of line losses, what about the outside of line losses, inefficiency at, I don't know, University of Calgary?
Oh yeah, exactly. Like that's the whole other, that's the additionality of it all, right? There's all the energy inefficiencies that happen at any manufacturer across North America, right? There's, yeah, it's probably $1 trillion challenge that we're solving for, really.
Thank you.
Yeah, thanks for asking.
Welcome, everybody. I'm just amazed in the last couple of days to listen to all of the speakers and feel like we are on the right path. And so I wanted to talk to you a little bit today about something quite different when it comes to data. There's been a lot of how do we quantify this? How do we understand the impact on people? How do we look forward? How do we model? How do we model more successfully? I think there was some questions about modeling earlier. And I just wanted to introduce something that we have been doing, a company I'm CEO and co-founder of for the last 10 years, and that is just kind of hitting its stride. And it is a version of SimCity, except for real. and for grown-ups, and has particularly gained a lot of traction in the energy sector as they woke up with us in 2019 and really discovered that they were in a disrupted landscape and they needed to be able to see forward. So you'll all probably be familiar with digital twins. There's a lot of initiatives and efforts in place-based intelligence and how do we see operational data. How do we understand and consume that easier, better in one place, and really look for efficiencies and insight, frankly. And we took a little bit of a step beyond that. So if you think of digital twins as the dashboard on your car, we're kind of like the people driving the car itself, the road in front of you, the changing weather conditions. We kind of make that dial forward and make everything plastic, so that not only we can see the infrastructure, the built environment, the systems that are in operation today, but we can also manipulate them. We can do virtual deployments, we can change conditions, and we can see forward and understand the impact in these environments on what we're building. And a key component of that, and I think I've heard this mentioned many times, is that we need to understand things from a human-centric perspective. So we also synthesize entire living hyper-localized populations. We have synthesized a lot here in Alberta, and we just won an award for that on Friday night, for Innovation of the Year for the Science and Technology Foundation. Thank you. Alberta's a hard crowd to win in, so we were really thrilled about that. But also, this population is really handy in a regulated environment because we are able to synthesize a population from never identified information. And we are able to dial that population forward then and understand the things that are happening behind the meter. So not only the way people are consuming energy, adopting new technology, responding to energy management systems, but we can also look at the impacts of these unprecedented scenarios that we're facing or considering, whether they're policy, whether they're environment, and we can look directly back all the way down through all of the critical infrastructure, through the built environment, to the people, and actually survey these populations. Our very first, out of the gate, they always say go big or go home, ask from the energy sector was in 2019, early 2020, from the Electric Power Research Institute. And it is also another interesting factoid for us is that the energy industry keeps asking us to synthesize them and then turn the lights out. So when there's a lot of conversation around here about resilience, we are deep into resilience. Almost everything we do ends up with a resilience question. But for them, it was they were facing something completely new. They'd lost the ability to forecast load very quickly because they realized that they weren't just pushing electrons, there was people at the end of their systems. They had moved, they were in their homes, there was critical industry that was shut down, there was a lot that was operating on backup power, there was a lot that was operating on backup staff, but load had shifted overnight during COVID. So that was a huge test for us, was could we actually synthesize the grid, the infrastructure, look at the load curves ahead of the movement and control order, so inform them of where the load was going to be coming from, right down to the individual address in Phoenix, and then could we turn the lights out and inflict a heat event on these poor people who are going through COVID, and tell them, the energy sector, what they could do about it instantly and quickly, but also in the long term, if these events happened again, where there was public health issues that were new and novel, and they needed to understand resilience from a human perspective. And again, we get asked a lot of questions about what happens when the lights go out by the energy sector. So, there's OEMs who are watching. We talk about how do we build decentralized energy, how do we build more resilient grids and communities, and what that means. There's also a lot of technology that's waiting at the gate. So they're looking at outages in Los Angeles, they're looking at new electric vehicle models, and they're waiting. They're trying to understand how they can actually deliver products into markets where the energy is not reliable. And then we get to do some really big, wow, that happened, virtually environments. So this was a coronal mass ejection event. So we talk about grids and we talk about microgrids and we talk about the issues of transmission and long wires and generation that's centralized. And then we start looking at what happens when unimaginable things go on. So for those of you who don't know, coronal mass ejection events are really bad solar storms, and we're in about a 150-year awkward cycle of the sun where if it's turned the wrong way and one of these events happen, we're all in trouble. And so we were asked to run these scenarios through a synthetic grid in Washington, D.C. with the Department of Homeland Security, handfuls of acronymed agencies in the U.S., and inform them if they mitigate, how they mitigate, what data they pass through these environments, and what that results for us. And I think a big part of it is decentralized energy. So that's the big stuff, the save our soul stuff, that when we're in this room and we're thinking about, oh, the markets are tough and the economics are tough, and just think about what happens when they can't replace those assets for 10 to 15 years. We get to every day. Most of our team has SWIPSI alerts on our phone now. If you don't know what that is, that's the space weather community warning us when there's something that's particularly interesting about to happen. And then this is something that we were just in Vancouver presenting. We were very fortunate to be able to look at a community in Nashville with the Tennessee Valley Authority. So, and this will give you a little bit of a deeper dive into what it is that's behind SimCity, except for real. It's not just play, it's a massive data and synthetic modeling environment. So with the City of Nashville, again, we get to bring really unique people in the room. City of Nashville, their community resilience groups, the Nashville Electric Service, which is the distributor, Tennessee Valley Authority, so one of the largest generators. We get to synthesize Nashville, and we get to synthesize all of their grid assets. We get to, and these are living, working models. We get to synthesize their circuits, their transformers, their houses, their people. And this is a 16-week project, by the way. For those of you who wonder, how fast can you do this? We can be fast. And then we get to synthesize all of their people. So 16,000 businesses, over, I think there was, almost 750,000 people, individual people, lives, livelihoods, economics, health, psychographics, you name it, and the built environment, which is critically important and a really unique intersection between people and the grid is the environment that they're living in their homes. And then we get to look at, when we synthesize all of these, what does that rack up to in terms of data? It's a lot. And so when we're looking at a full diversity of population, when we're looking at resilience environments and the difference that decentralized energy can make, there is a lot of people that have a lot of intersectional conditions that we need to pay attention to, that rely on energy in different ways, that heat their homes in different ways, that have backup heating. So I have, grandma has her little plug-in heater that she uses, and somebody else has strip heating still, even though their heat pump was left in an install mode. And we can really begin to look at how all of these things actually create incredibly emergent behavior during a scenario. And it also makes a difference, these scenarios, how long they last. So a scenario can be 24 hours, 3 days, a week. Resilience in those different time periods is dramatically different. And dramatically different for different populations, dramatically different for technologies. I think we had, they were talking about the generator that went down after 24 hours or during an operation. All of those things interrupt different things at different points in an outage. And it's really important to understand how we use technology to compensate and when we use it and what type of technology is appropriate given the impact that we're dealing with. And then the next step that we get to play and the role that we get to play when we create these massive environments is we get to show people. So everything is visual. We are visual creatures. We need to see things. We need to see our own community. We need to see forward, and we create a holodeck, we call it. It's our visualization platform. So you can actually run these things forward, and you can't unsee them, which is part of the compelling world that we live in. And these can be used to communicate across boundaries. So they're accessible. They become accessible to the community, they become accessible to the stakeholders, and they become accessible to the designers and engineers as well. And in this case, we looked at, okay, now that we understand what's happening with the grid, what's happening on circuit levels, who's managing power, load shedding based on revenue models instead of social impact, how can we bring these things together and look at where does community resilience meet the needs of the community and where does it fall down? And these are opportunities for DER like crazy in these communities. And this is one of the places where they're investing in them outside of market and economics that are traditional, because they're investing in them because they know if they don't, this is going to be the cost of the next big outage. We have some great initiatives going locally. This I would just wanted to show you because it's lots of fun. Is one where we have regional advanced labs up and going. In the Edmonton region, we actually have 14 cities that are participating, and we're dialing forward their futures and looking at all different aspects of population growth, a V-grid, but also land use, consumption, water consumption, energy, affordable housing, you name it. And workforce is also important. So because we can synthesize populations, we can also synthesize the workforce that's going to be required for all of these, and the opportunities that we have with post-secondary institutes and with industry to make changes in that workforce that we know we're going to need to make it more sustainable and to meet the needs of what's coming. And we were really honored to win the Aztec Award on Friday because it's local. But we have been basically around the globe and been so fortunate in the acclaim and the applications that our environments are being used for. Almost all of them connect directly to energy and energy futures. And that's me.
Excellent, Myrna. Thank you so much. Now we've got 5 minutes of questioning. So that, actually, we have 6.5 minutes if we wanted to. So those microphone runners out in the audience, does anybody have a question for Myrna? Yes, we have one right here. And there's no runner running to you with a microphone. So just blurt it out.
Basically our democracy. I'm already afraid of my own phone, knowing when I'm getting up, going where, what are my purchasing habits are. And so I'm seeing on these slides that you are capable of saying that this is a pregnant lady and the other one is going with a stroller, slower and whatnot. For the purpose you have, this is fantastic. But there should be some sort of ethical argument here that how we can protect this data to be used against us. So that's my concern and question.
So just to give you a little bit of context, we are very selective about the customers we work with. And yes, it is our concern, exactly the ethics. You have to remember, we don't base what we do on surveillance data. So we synthesize our populations off of absolutely aggregate and publicly available data. But we do it in a way, so there's somebody living in your house in our synthetic universe, but they're not you. But they're close to you. But if you look at a block level of the people living in that block, they'll be pretty representative of your neighborhood. If you look beyond that, if you look at a city level or a block level, or a census tract level, we're getting really accurate. But the important part is that that accuracy is not generated from a violation of your contract for your personal data. It's being used by people who are facing some of the most unprecedented horror shows that they are trying to get in front of to solve us, including decarbonization, including climate change, including black sky outages, including, so if you want to give those people, you know, that kind of license to be able to not use your data at all. And this is why they are so excited, because this is the first time they can step into a room and actually living lab, because this data is available, it's synthetic, and try and actually solve some of these things. That's the important part about this.
I want to follow up on this point, and thank you for that explanation. If that's the case, if we now are capable of doing synthetic cities, which
Yes.
then I would think we can do synthetic provinces and we can do synthetic countries.
We are.
Yep.
Yep.
Then why can't we pass a regulation that says, Microsoft, you can't have any data. You can't collect it from us individually. Because what's the need?
We have a big problem with surveillance data for exactly that reason.
Why?
Yes, because there is no social contract.
Yeah.
Yeah.
But so my point is that if this exists, and all the reasons that Microsoft or anybody else collects your data because they want to sell it for marketing purposes or this or that or anything else. Oh, yeah, sorry.
It's not there just for show.
Yeah, sorry. If this, you know, if this is all possible, then why do these companies have to collect specific data from people under, you know, this 3-page contract you're supposed to sign that nobody ever reads, and then collect that data as a surveillance data?
You'd have to ask them, but I call them the data damaged. So there is a universe out there that still believes that they have to collect every data point.
Yeah, okay.
It is incomplete, it's biased, it's historical, it's irrelevant, it's disconnected, it's siloed, it's regulated, it's under GDPR in Europe. It is, and yet they are still thinking that they can gain that mastery and that insight from that load of crap. So, so I call them the data damaged, and
Yeah.
and so this is why you saw that list of awards. Why a small company that started in Edmonton, that's a certified Indigenous company, that's women-led, is now on the top of the world stage.
Thank God.
Woo! Yeah, well done.
All right. Thank you, everyone. I appreciate you having me here at the forum and appreciate this chance to chat. Mixed chat and talk there at the same time. My name is John Neufeld. I'm a partner and a co-founder at Gnosis. We're really leaning into the whole silent G thing. We also have a product called Node, which is a silent G. It seems kind of fun, so we may as well. I'm going to chat a bit about the power of data and a bit about what we do and some of the case studies and some of the work that we work on at Gnosis. We have a number of companies that we are associated with, that we work closely with, who really help us put together a viewpoint from the sky all the way down to the ground. It gives us the ability to capture data at different scales, at different resolutions of different types. And then, of course, to make something of that data using complex artificial intelligence algorithms and custom engineering. So we work across the scale from space all the way down to that machine learning and digital twins kind of arena. Each one of these companies does something different. I'm not going to get into those specifics necessarily, but I'm happy to chat with anybody afterwards if you do want to get into some of those specifics. The customers that we work with tend to be companies who create, produce, utilize, consume large amounts of spatial data. Everything that we do revolves around knowing where something is and using that to solve a complex problem. In particular, we're interested in working with utilities, energy providers, people who need to manage three-dimensional data about their facilities, about their systems, about their interconnected pieces of equipment. We've been doing a lot of work lately using LiDAR data, whether that's from an aircraft or from a terrestrial vehicle. And there's a lot of uses for that, right? You can monitor health. You can look at your inventory. You can keep track of what you have. You can manage your risk. And of course, you can manage your engineering design and make sure that things are working really the way they're supposed to be. I don't need to tell you, you guys understand this. These are complex, large systems. They're difficult to manage and can get very expensive, right? In terms of a data system, you want to make sure your data system and your knowledge and your digital twin is easy to use, is not super complex, and is not super expensive to scale. That's really critical. So our vision as a company is to be a leader in digital twin technology, in monitoring of critical infrastructure. We recognize, you as energy producers or energy creators, and we've been hearing it all week, right? We're concerned about reliability. We're concerned about consistency. We're concerned about accuracy. We're concerned about scale. And of course, everyone's always concerned about cost effectiveness. At the end of the day, you want to make sure there's more dollars coming out than there is going in. Otherwise, it's really just a poor hobby. It's not really a business anymore. We've been talking a lot about decentralized systems. Obviously, it's right in the title, right? And in the conversation, we've talked about decentralized energy systems and the ability to disaggregate the production, transmission, and consumption of energy. And I think there's a lot of power in that, right? If you can take the energy production and consumption, put them together, and co-locate them, there's a lot of value, right? If you can decentralize the way that your systems are functioning, it gives you better resiliency. It makes things more robust, and it makes them less prone to single points of failure. If your one large plant goes down, you experience a large failure, right? If your one transmission line goes down, you experience a significant failure. But if you can decentralize that, it makes your system much more resilient. Now, why am I telling you something that you already know? Excellent question. I think the same thing is true about our data systems. If you keep all of your data in one place, it becomes much more subject to risk. So if we're going to decentralize our energy systems, why don't we decentralize the way that our data is stored and managed and used and accessed as well? So I think that's a great idea, obviously. The way that we operate, we provide cloud-based solutions for managing and storing all of this data so that your users can access it anywhere. We're currently working with a large transmission line company. Sorry, not the transmission line company, the engineering company that works with the transmission line company to manage their spatial data. And one of the key things is their distributed workforce. So all of their workers are not sitting in one lovely office, in one lovely town, working together in the same physical space. Their workforce is distributed across the province and across the country, but they still need access to that same data. So by decentralizing the way the data is stored and managed, it makes it much more accessible to the workforce to be able to do what they need to do. Instead of shipping hard drives across the country, you can simply access it through the internet, right? It becomes much faster, much more usable, much more valuable. We talked about resiliency earlier, and I think resiliency is knowing where your assets are. I think it's important to know where your assets are. We talked to another company recently who said, look, we're embarking on this big project. We have our GIS data layer, but we found out after 6 weeks of work that our poles and our lines aren't where we thought they were. Yeah. And I was like, I'm sorry. What do you mean they're not where you thought they were? They're like, yeah. Like we sent a crew out, they did a GPS survey, and it said that the power lines and the systems were here, but my geospatial data layer says they're over here, right? And it's not a big mismatch. We're not talking like kilometers. They didn't go out in the field and be like, I don't see it, right? It was there, but it was a significant mismatch, which then leads to inaccuracies in their modeling, in their forecasting, and in understanding what they have. So now we're talking to them about how can we use existing spatial data and how can we use existing things like satellite imaging at super high resolutions to extract things like poles and wires. What can we do to help you understand where your assets actually are so that when something goes wrong, something doesn't go the way you expect, it becomes much easier to recover and to rebuild and to get things back up and running again, right? It's hard to be resilient and repair your systems if you don't know where your assets are. I think digital twins really enable smarter decisions, right? So here's an example of some work that we've done lately. You can see the one image there includes the classification, right? So we've got a LiDAR scan. That's from an aerial system, so a helicopter or an aircraft. And you can see the automatic classification there that's been done. You can see the buildings, you can see the power lines in blue, you can see the vegetation in green. You can even see that one little spot there. Maybe it's a bit hard to see, but there's a little bit where the yellow goes over the blue line. That's probably vegetation encroachment, right? So now you've got trees growing into your power system, and that's a serious problem, right? Whether that then is at risk for fire or of causing problems with your lines due to high wind and those trees falling over, that's a significant problem, something that should be flagged and dealt with properly, right? The next step then is building out your entire electrical network, understanding how the topology of things connect, how that all fits together, and where they are, right? The next step down the line, of course, is that feature extraction model. I'm going to jump to this one because I've got the images a little bit bigger. So this is the raw scan from a mobile LiDAR system. This is a laser mounted on a truck that somebody drove up the road and collected all of this data with. The laser pinged off the pole, it pinged off the wires, it pinged off of all the equipment on that pole, right? So we can see it all in that laser return that's been colorized by an image that was co-captured. Through an AI system now, we're able to extract the information about what's on that pole, where the wires are, what's going on in that system, right? And then the next level is to automatically turn that into an engineered drawing. And then the next level is to extract all the dimensions out of that. So all of this information, it has been produced from that single LiDAR scan, driving the truck by at probably 40 kilometers, 50 kilometers an hour, collecting millions of data points per second, and then transforming that through artificial intelligence to gain information, to gain knowledge. And I think by collecting all of this information, we're able to transform from business as usual to a really informed and aware sense of where our assets are, how they're doing, what their health is, and what sort of actions we need to take. Another key point I want to talk about is, how much is leaking out of all of these facilities? And do we really know how much we're emitting? In particular, I think methane emission is a significant issue. And I think there's a lot more methane being emitted than many people are willing to admit or to say out loud. We spent this summer working on the Methane Air campaign. This is through the IO Aerospace company. We have a modified Learjet 35 that we operate. So we bought a beautiful business jet, and then we cut 2 giant holes in the floor. I should put those pictures up. It's terrifying. You can see right through the bottom of it, actually. And you're like, I'm going to get in that thing, and I'm going to fly around? Are you sure? Anyway, we cut 2 giant holes in the bottom of the jet, and then we filled them back in with payload bays. So we have the ability to carry 2 payloads at the same time. And those instruments look through 2.5-inch thick silica glass. So we carried an imaging spectrometer in the jet. We flew it around at 40,000 feet. And we captured 750,000 square kilometers of methane emissions data across the continental United States and throughout Alberta. For perspective, that's more than the entire province of Manitoba. It's amazing what you can see at 40,000 feet at 400 knots. You can cover tremendous amounts of territory. We covered about 10,000 square kilometers per day this summer while we were out there flying that campaign. And the data is still being processed, so I don't have a number to give you, but I can tell you that the methane emissions that have been discovered from that were far more than what was being reported and than what was being expected, right? It's another way of using location-based spatial information to derive understanding and knowledge and insight and transform the way that business is being done. Ultimately, we live in a connected world. We're talking about decentralizing. We're talking about interconnecting. We're talking about building systems that are resilient, that are technological, that are future-proof. That requires connections, right? It requires digital connections, it requires data, it requires understanding to flow back and forth. And I think as an industry and as a group of practitioners, we come to rely on that data to know how our systems are functioning, to know what's being generated, what's being consumed, what's happening at the macro level, but what's happening at the micro level. We live in a connected world, and more our success will be driven through connections and through the data being delivered and understanding how our world works. Thank you.
Well done, Jonathan. Well done. Well done. Thank you very much, Jonathan. That was really good.
Yeah, thank you, Brian.
Very interesting. And again, we have time for some questions from the floor. We have our microphone runners ready to dash into the crowds as the questions begin to flow forth.
Usually the first question is, can I go for a ride in the jet? And the answer is probably not.
You talk about different scales of data and different resolutions. How do you calibrate from the very broad scales down to a very fine granular scale? Is there a way to improve the accuracy of, say, your jet level with your ground-based systems?
Yes, yeah, good question. And I think so. There's really good ways of overlaying spatial data because it's all tied together by geography and by position. You can use the higher resolution data to kind of up-res the lower resolution information. In particular, if you're dealing with multi-band information. So say you've got the black and white imagery at 15 centimeters and then like hyperspectral or thermal imagery at 2 meters, it becomes very easy to kind of up-resolution that data.
Just one quick follow-on to that. Can you use machine learning to calibrate those two different levels together?
Oh, I mean, I think you can use machine learning for anything these days, can't you? Yes, for sure. I mean, machine learning is really pattern recognition and pattern generation. My favorite machine learning joke is a machine learning algorithm walks into a bar and the bartender says, "What will you have?" And the machine learning algorithm says, "I don't know, what's the average of everybody having?" So absolutely, you can find those patterns, you can understand those patterns, and you can dig through the data with those algorithms to find out, what's happening there and how to calibrate the two together.
Excellent. And another question. Yes, we have another one over here.
Yeah.
Hi, this working? I'm just trying to understand, I guess, the scope of the work you guys provide. Do you just acquire the LiDAR or approach the people who have LiDAR, they acquired some other means and then perform the analysis? Or do you also do LiDAR acquisition right through to analysis?
Yes, we do all of that. So if companies want to acquire LiDAR, we can do that. We have the equipment and the technology and the people. If organizations already have an incoming stream or a preferred partner to do the data collection, we can work with them on the analytics, the production, the deriving of the insights out of that, and then potentially even the creation of the machine learning algorithms.
And then just to follow up, just kind of maybe a geek question, but just wondering what kind of, so you mentioned making this data through your cloud-based system available remotely, and I'm just wondering what kind of software you run, assuming you have high-powered servers to run, because I've seen, these point clouds, you can slow down your machine pretty quickly, but just wondering, so you have these supercomputers running your cloud, and what kind of software do you use for these GIS point clouds? Is that what you're giving them access to, or?
Yeah, for sure. So we have one of the best supercomputers in the world. It's called AWS. All you have to do is pay them money, and then it scales to however big you need. It's remarkable. So we host all our stuff on AWS. We've written our own software to automate, manage, and handle the LiDAR data processing and serving. And that's a combination of code we've written in-house, as well as the fantastic open source libraries that exist already out for that sort of stuff. When companies or when individuals pull that data, they have access primarily to the processed, colorized, classified LiDAR information to be able to work with that. Or we can even give them the next sort of digested step, which would be vector layers if that's what they're looking for.